it's me first. Just, yeah.
Hello, test. Hello, test.
Okay. Again, welcome after the lunch. I hope you are not so tired that you can follow the next presentation done by Marsh and Steve Dispensa. They were talking about SSL and TLS, one topic that was got very famous last year because some kind of new attacks were discovered. And I think it's a very, very interesting topic, but get all the exciting stuff from Marsh and Steve. So,
thanks.
Enjoy.
Well, welcome. And if you do fall asleep, try not to snore, I guess. So I'm Steve Dispensa.
I'm Marsh Ray.
And we're going to spend an hour talking about a little bit about the history of the auth gap bug, and then more probably about some related topics closely related to authentication and SSL in general. Probably spend a little bit of time talking about the attacks. This is going to be mostly like a two-person panel discussion, more than kind of a streamlined slide after slide. And
we work together and we argue a lot, so you might see that come out.
So I'd like to see if there are questions, please just raise your hand in the middle, and we'd be glad to take them.
Just yell out.
Whatever works.
Make it interesting.
Okay. Take it away, Mr. Ray.
Well, I'm Marsh Ray. I'm a software developer. I was working on some of our software at Phone Factor, and I came across a bug in SSL, not just SSL like OpenSSL, the library, but the protocol itself. And as a software developer, it interests me to think about how these things get engineered and how bugs might get engineered, and how something like this might go undetected for 14 years or so. Now, all presentations like this are required to have a stack diagram. Basically, we have TCP/IP at the network layer. TLS is a protocol that's intended to provide secure transport. It was originally called SSL for the secure sockets layer, and that's what people wanted, was a drop-in layer that they could put on top of SSL that would make their existing applications magically secure. I think Sergey was talking a little bit about that this morning, and I think that we're going to echo a lot of the things that he said. We're really on the same wavelength about this. So you would typically get your SSL from an SSL TLS library like OpenSSL or GNU TLS. If you're a Microsoft programmer, it might be S-Channel. And then some of the other larger corporations and browser vendors tend to write their own. On top of SSL, you would be calling it with an HTTPS library if you were doing web work.
This is like mod SSL in Apache, or the SSL filter in IIS or something. The thing that connects the dots between an app layer protocol that's not supposed to have to know anything at all about SSL and the OpenSSL library, which at least needs one function call to turn on SSL. And
so Steve asked, why didn't I write HTTP library? Because it's essentially HTTP layered on top of SSL. But there is a bit of code in there that relates HTTP and SSL. And there's even, SSL TLS is defined by an IETF RFC, but they have a different RFC number for each protocol that specifies how to do things like check the certificate in a way that is appropriate for that protocol. And then, of course, your application code runs on top of that. So what I found was a man-in-the-middle attack against SSL TLS, and that attack comes from an authentication gap. SSL TLS can renegotiate, but the session before the renegotiation and after are not strongly bound together. There's nothing that cryptographically ties them together. So we're going to talk about, this is sort of an overview slide. We'll talk a bit about an overview of TLS, how it's discovered, what some vulnerable code is, and the different mitigations that are options for fixing it.
Can I just quickly break and see, was anybody at ShmooCon this year or seen the videos? So we did some of the stuff that's not in this talk is now online at ShmooCon if you're interested in the gory details of the backstory. Mostly we're going to try to stay technical here.
Yeah, and I didn't set my notebook up for a demo right now, but just come find us sometime in the next couple days, and I'll be glad to give you a demo, or we can try it out on your site. Okay, so as we said, SSL was originally the secure sockets layer. It was invented by Netscape in 1994. They had something they called version 1, but it never escaped the lab. Steve, you're more of an expert on the internet protocols and their histories, but we weren't able to come up with a lot of examples of existing practice in the public sector for something like a cryptographic data protocol back in 1994.
Yeah, I mean, I'm curious. What do you guys think of this? What do you think in 1994 was the closest kind of prior art to SSL? Anything jump to mind? I mean, this is pretty new stuff. Is the point? I personally, we just came up with this concept last night over beers or something. So.
We couldn't think of anything either.
Yeah, mainframes or something. I don't know.
So the guys at Netscape who were developing this, they were software engineers. You know, bless their heart, they're doing their best. And but obviously they weren't formally trained in cryptographic protocols because very few people outside of the military were. Something they called 0.2 of their spec was the first thing that shipped, and it's known today as SSL v2. That spec was revised a few times. You know, I count 5 times in 4 months.
And those are the ones we know about.
Right.
I mean, seriously, we'll get to SSL v3, but it's very clear that there was not a rigorous document management policy going on here back in the Netscape days.
Right, which is probably a good thing, you know, that they were able to rev it early. It probably improved quite a bit over these revisions. In SSL v2, I'll just go through the messages here. The client initiates it with a message from client to server called client hello, and it contained a challenge value and the cipher specs that the client supported. Then the server would answer with a server hello message that contained a connection ID, the certificate of the server, and the cipher specs that the server supported. The client would respond with a client master key. This master key would be encrypted with the server public key from the server certificate. The client would send a client finished message, which was essentially just the connection ID that was encrypted with the client write key. And the server would reply with a verify that had a challenge to the client and a new session ID that the client had the option to remember. And these were encrypted with the server's write key. Other features of SSL v2 was it only used the MD5 algorithm as a pseudo-random function, and for Macs, ensuring the integrity of the application data records. The client finished message back here was simply an echo of the connection ID from the server hello, so that was known plain text. The server finished message is the session ID data. That's the last one here. But since this is all new information to the client would have no way to validate it or know if it had been manipulated. And so the man in the middle could freely manipulate many of the fields in the SSL v2 handshake. What it did provide was mandatory strong server authentication. So the server was required to present an X509 certificate and prove that the server knew the private key to this certificate. Optionally, the client could supply a certificate, but that to this day is not a capability that's used very often. And then the U.S. had export regulations which limited the strength of the cryptography that could be used in products that were exported elsewhere in the world. So it would send part of the cipher key in the clear, just to make it weak. You want to talk about?
Sure. So all those issues you saw the document history, right? I mean, there were 5 or 6 public revisions, and Lord knows what else going on. But there were some very serious issues with V2. So V3 emerged. I'm actually going to not belabor too much of the point here. One really interesting thing, though, is, and this will come back when we talk about how the auth gap that we found was fixed ultimately using extensions. That last point there, the SSL v3 did not allow any extension of client hellos. That's actually document dependent. I think, isn't that on some of this on the next slide?
Yeah.
Or 2 slides. There we go. So I'll come back to that. But the upshot is that this version of SSL v3 did not actually allow for any extension, and so a well-meaning implementer would, of course, break if it did see anything with client hello.
But there's still disagreements about it because they mixed up, they had different versions of this document that got circulated.
Yep.
This was the end of it for Netscape. At this point, they kind of put this spec out and abandoned it. And then Netscape kind of fell apart, and they got parted out and sold to different companies.
This is around the time IEv2 or I guess it was IEv2 shipped in
Internet
Windows
Explorer
NT, and
2, yeah.
And then IE3 shipped shortly after that, and that was the end of Netscape, unfortunately.
So this is a very old protocol, SSL v3, but we did talk to somebody at a company who makes, core networking
at F5,
boxes at F5, yeah. And some of their samples indicated that SSL v3 still accounts for 22% of SSL handshakes on the internet. We suspect a lot of that is Windows XP, which is still shipping, and it defaults to SSL v3 even though it can do the newer version of TLS. This was the other document that was available, but it did explicitly allow the client hello message to be extended.
So this was a real argument. I mean, we got into this implementation workshop at Google. We were arguing about how to fix this, and following that, there was one of the guys who was CubeMates, I think, with the guy who owned this spec was part of this working group, and even he was a little bit confused on exactly whether or not v3 explicitly allowed for client hello extensions and should be coded as such, or explicitly forbade client extensions and should be coded as such.
Yeah, as a software engineer, I was kind of wondering, how would something like this happen? And my prediction was that the guy who wrote the Netscape server software shared a cubicle with the guy who wrote the SSL protocol, and so the two of them were able to exchange information without it being documented on paper. Later on, we did get to talk to some of the people who worked in that office at the time, and they weren't exactly cube mates. They sat at different cubes, but they were brothers. SSL v3 was a completely breaking change. It reformatted the client hello message completely, which was, probably a useful thing to do. However, there were a lot of servers out there that would just hang if you sent them a new version of the SSL v3. So the SSL v3 and later specs even allow you to send an SSL v2 hello message just to be compatible with them.
A lot of your software today, if you go look at the SSL config screen, will use old style SSL hellos.
Especially if it fails the first time, it'll retry with an old school hello. But the best thing about SSL v3 is it defined a consistent record layer. So the record layer would define different types for handshake data, your application data, and alerts. Previously, the SSL v2, it would send handshake messages, but then once those were done, it would just send application data, and there was no real obvious way to tell which was which. And it would modify the cryptographic parameters after each message went along, whereas SSL v3 improves on that by negotiating with a handshake and then sending one message to switch to the new set of negotiated cryptographic parameters.
A lot of hard-coded defaults. I mean, I think, let's keep moving.
So, the new message introduces a new message, the change cipher spec, which switches to the pending state all at once, as I mentioned. And it has a new message for finished, which is exchanged in both directions, and that is a cryptographic hash over all of the previous handshake messages up to that point as seen by that endpoint.
Right.
So in that way, that can resist a man-in-the-middle attack by each server sending what it saw as how the handshake went.
Well, so what that concept of a structured record layer enabled was the idea of going from protocol negotiation to data flow, back to protocol negotiation, back to data flow in a structured, organized way. And so very naturally, this concept of renegotiation emerged. And that question, who knew, is not just a guess. I mean, really, a lot of people didn't know. In fact, I'm curious, show of hands, who didn't know that SSL did renegotiation like this? Anybody? It's like 50-50 at security conferences. You can imagine what it is in the general programming community. So it's a great idea. It uses exactly the same handshake messages as for renegotiating connections it did to negotiate the original connection. And in fact, it even allows for the frightening and, I am certain, under-tested capability of interleaving these data and handshake messages even at the same time. Not just going from data to handshake, back to data, but doing both at the same time.
And this is extremely helpful if you have a space probe in Jupiter sending back high-speed data. You don't have to delay the data transmission for several round trips during this renegotiation.
New server message. So they did, the spec authors did recognize that renegotiation happened. They explicitly allowed for it. And the idea was that the server would be able to ask the client to renegotiate for a variety of reasons I think we'll get into in a bit. And so there's this new message called hello request where basically the server tells the client, I'd like you to renegotiate. The client is free to ignore it, actually, in which case the server might disconnect them or something. But at the end of the day, the actual renegotiation is done by the client sending a brand new client hello, just like the original client hello. You see those 5 words there, or on its own initiative. Something that was really not well appreciated, even among TLS people, was the idea of client-initiated renegotiation, where the client can be doing his thing and then, for any reason or no reason at all, can just send a new client hello and start a negotiation. And the best part about it is that servers that implement renegotiation don't tend to keep, and this is implementation detail, so it'll be dependent, but they don't always strongly associate that hello request that they sent with, okay, now I'm willing to renegotiate. In fact, the default is that they are willing to renegotiate, period, if you're on OpenSSL, which is not exactly a corner case.
It depends on how enthusiastic and helpful and complete your vendor was for your SSL library and just the accident of the design of the API that it uses. But a lot of them will just handle all this renegotiation for you transparently because, after all, the application author wasn't expecting it to ever have to worry about it. So after Netscape melted down, they handed the spec over to the IETF, who promptly renamed it to be TLS, but everybody still calls it SSL. They improved the design a bit. They defined this abstract pseudo-random function, which replaced an odd assortment of MD5 and SHA combinations that were used in SSL v3. And it does it in such a way that if either MD5 or SHA are broken, then the protocol itself should survive that.
One of the, just before you jump off the slide, we skipped it before, but this plus the shortening of 3 bytes to 2 bytes in the SSL v2 to v3 cipher spec, are 2 cases where somebody intentionally shortened a protocol field in a subsequent rev, which is pretty darn unusual, particularly in something that looks like it adds security, going from 36 bytes to 12.
Yeah, and so now that the finished message is 12 bytes, that's 96 bits. And so the birthday attack against 96 bits is 48 bits, which is well within the range of feasibility for some attackers. And you heard that here first, guys. June 2003, the IETF finally gets around to defining some extensions. Various versions of the spec had kind of had this one-sentence carve-out saying you could tack on extra data. But it's 4.5 years after the fact. Nobody's had any products that use these extension fields. And, guess what? As soon as you start trying to send extensions to something that wasn't engineered and tested for it, it'll crash the servers. And it didn't work with SSL v2, which is still widely expected. Newer specs add new versions of TLS and more extensions, but up until like last week, the vast majority of SSL connections on the internet were not using extensions for anything really critical, even though there's some real economic cases to be made for certain extensions, like being able to support multiple HTTPS sites from the same IP address.
Okay, so back in the early days of Positive Networks, which was the name of the company before we changed it to Phone Factor, I guess, I became aware via the IPsec working group of this paper, Tunnel Authentication Protocols, and seriously, go read it if you haven't. It's really kind of a cool paper. I think it was 2002 that it was published. And it makes a general point about the fact that when you've got one layer doing some authentication and another layer above it doing other authentication, that it's actually a lot harder than it looks to tie them together. There are possibilities for man in the middle.
This is exactly what Sergey was saying this morning about composing multiple layers of the protocol, that the complexity of the combined is greater than the sum of its parts.
Right, exactly. So at any rate, we had this in mind from the early days. Marsh and I were talking about this in June or something, and anyway, so file that idea away. And
that uses an example of EAP, PEP, to show that if you could convince the client to conduct its authentication unencrypted, then you could perform a downgrade attack on the client, and the server would still look like it was encrypting, or vice versa. So jumping to one example that they use in this paper, which was very close to the actual bug that I came across, is the HTTPS login form, where the client strongly authenticates the server. The server's forced to produce the correct certificate and prove that he has the private key to it, and the server authenticates the client with a username and password passed with an HTML HTTP form.
In other words, like two layers in the stack above where the server or the client auth the server.
So in that sense, it is mutual auth, and it's at least strong in one direction. The client verifies the server cert through his set of trusted root certificate authorities. The client uses that cert's public key to pass the session key. And so the client simultaneously authenticates the server, and this defends the session against a man-in-the-middle. So the session key that's used for the encryption is strongly bound to the certificate that the client decided to trust. The password credentials are passed over this encrypted channel. So in that way, the client or the user authenticates to the server, but the session key is not strongly bound in this direction. So the client proves that there's not a man in the middle using the PKI, the public key infrastructure. But the server has no way that he can prove the absence of a man in the middle. He can only rely on the client to do a good job of this. So what if the client is a bozo? What if the client trusts an evil root CA? A typical Windows or Firefox machine will have about 200 CA certs that they trust. So in this model, the server has to rely on the client to prove that there's not a man in the middle. So the server ends up transitively trusting every root CA that is trusted by the client. And it's even worse than that in the sense that the server can't know exactly which CA was used by the client. So the server can't even go back after the fact and decide and know anything about how the client made his determination that there wasn't a man in the middle.
It's actually even worse than that in one sense. That let's say that the client, let's say if one of those 200 CAs gets compromised, and somebody comes up with the signing certificate for, easy super duper SSL
that would never
incorporated.
Happen.
That would never happen a year and a half ago. And at that point, you would say as a server admin, well, I simply won't trust clients that are, still relying on that cert. There's no way to tell. Absolutely. So somebody gets owned, and you have no way, you have to hope that every client connecting to you has patched and disabled that cert.
And as Sergey was talking about, these are issues of that graph of trust going on. But I just remembered this quote from long ago. I installed PGP years ago, and I always remember this quote. It left an impression on me that trust is not transitive, or it's not supposed to be transitive like that. I have a friend who I trust not to lie, but he trusts the president not to lie. That doesn't mean I need to trust the president not to lie. But really, to have what you really need is strong mutual authentication. It requires that each endpoint be able to independently prove the absence of a man in the middle. And because this HTTP form authentication is just carried through a TLS connection that's authenticated in one direction, it doesn't provide strong mutual authentication. And so this attack goes a little bit beyond that paper that we mentioned earlier, because in this case, neither the client nor the server needs to be downgraded to unencrypted communication. But if there's one point that I want people to take away from this presentation, is that if you run an SSL website or SSL web server, you are literally trusting every root certificate installed on every client that connects to you.
Unless you're using strong client auth with certificates.
So let's look at a packet capture real quick.
Any questions at this point, by the way? All right.
Okay, here's an example of the attack. .17, where is it? Yeah, .17 is the client. .125 is the man in the middle. No. And I think I just captured the server perspective of this. Okay, so this is how it's seen at the server side. The server sees the initial client hello. The server sees the server hello, certificates, server hello done. This is all very normal type of handshake happening. Then this is a client-initiated renegotiation that the server sees, where the client hello is the first message. If it had been a server-initiated renegotiation, there would be a hello request message right before it. Let's see. In this case, the server is seeing a typical web request. Except that first session before that renegotiation was actually the attacker who connected to the server, injected this text up to this x-ignore header, and then didn't terminate that line. So then the client's legitimate request comes in, from the perspective of the server, that is, as being effectively commented out, because the HTTP spec says he should ignore this header that he's never seen before. And then the attacker can steal whatever cookies that the legitimate client is sending right now. Then here's the server's response, but it's not really relevant. The interesting point here is that the attacker gets to supply whatever request he wants to inject on behalf of the legitimate client and steal the cookies at the same time.
So a couple of points on that, actually. Well, okay, you already get rid of it. One of the things to remember is that, so that's a get that Marsh showed. It could just as easily have been a post or a put or anything else. And in fact, it's kind of a lot scarier if it is, depending on how it's authenticated, because now you're really talking about specific transactions. And one of the things that a lot of analysts were saying when we published the paper was, well, the good news is this is just a whole lot like cross-site request forgery. So everybody's got CSRF mitigations in place, right? So this shouldn't be that big of a deal. The reality is it's not. And one of the ways in which it is not is it can be any verb easily. And it can I don't know if we have the Twitter thing in here. Maybe we'll get to that later. But there are even attacks against places that did have CSRF defenses deployed that don't work for one reason or another.
Yeah. So somebody demoed this against Twitter, and they showed how it could make you tweet your own password. Okay, so is it really a problem with the TLS spec?
Yeah, this is a question that every single person we talked to asked, and then I guess maybe with two exceptions. And then eventually we all sort of answered it the same way. So the question is, maybe HTTPS is just doing the wrong thing. And in fact, there was a pretty well-known, at least in his circle, published cryptographer at one of the major vendors who, after 8-hour meeting or something when we went through this, was still convinced that the problem was not actually with TLS. The problem was simply that every single user of TLS was doing it wrong.
Well, he said the problem wasn't with the crypto itself, it was with how people were using it. But this was a recurring phenomenon that we saw, that engineers, the closer that they were and the more familiar they were with TLS and the details of that specification, the less likely they were to know anything about how people actually used it in practice.
Right.
I mean, I think if you were an application developer, you were thinking you were coding to a secure sockets layer, whereas if you knew a whole lot about the TLS spec, you knew that it could renegotiate, and you would be foolish, to expect otherwise. So here's some example client code. This is not any particular language, but it's the kind of thing that you'll commonly see in applications that are doing their own SSL type of work. You have a DNS name, you resolve the DNS name to an IP address, you connect a TCP socket, then you call your SSL library.
This is like GNU TLS handshake or start handshake or something.
Yeah, or OpenSSL has some more code. You connect with SSL. Once you're connected, you look at who's the peer cert on the other end. You look at the subject name of that cert, and if it's not the DNS name that you asked for, then you throw an exception or you abort the connection somehow. And if it does check out, then you go ahead and you exchange your critical data. So what's wrong with this client code here? I contend that there's nothing wrong with that code. That code was secure with SSL v2.
As secure as SSL v2 was, that code was secure.
Right. It silently became vulnerable when renegotiation was added with SSL v3. And SSL stacks started transparently handling this renegotiation for you under the hood. But it could be made secure again by disabling renegotiation with a patch for your SSL stack. So I think that shows that the fault does lie unequivocally in the SSL TLS layer. Another interesting thing is I don't think there's any tutorial on the web that says, here's how to use our SSL stack safely, and it gives actual example code to copy and paste from that does everything correctly. To me, that says that there are a lot of apps out there that aren't doing everything correctly. And, as an example, I looked at all the Perl bindings for OpenSSL. And so in order to do this securely, you pretty much need to have callback functions calling back into your application logic so you can abort the handshake, rather than this line here where he calls the get peer cert after the handshake has already been conducted. Well, you don't actually know that there hasn't been a renegotiation between here and here. It's a race condition between your code and the attacker, and the only way to defeat that is to have a callback within this handshake. And, bless their hearts, the guys who were writing these Perl bindings to OpenSSL couldn't get the callbacks to work entirely right. And you can kind of see their struggles in the documentation. But, that says to me that probably all Perl apps that use SSL TLS directly are vulnerable to one attack or the other.
Sure. So the good news is there is a solution, and it's in the newly standardized RFC 5746. There's a little bit of information in the RFC about the attack and some pointers to the original paper. But the good news is once you're patched, and both the client and the server have to be patched because Otherwise, you're still completely vulnerable. But once you're patched, all of a sudden, you're not vulnerable again. So, it was observed at the Google meeting that, you were likely more secure you're certainly more secure from this attack with SSL v2 than you ever would have been in v3 until we added the renegotiation.
Some of the worst attacks against SSL v2 were like you could be downgraded to triple DES or something horrible like that. Which are worth moving on from that version, but not as bad as a known injection attack like this. We need to cover certain terminology in TLS. We'll make it quick, but this is kind of an important point when we're looking at the history of this bug. There's this term called a session, which is what results from a handshake taking place as a set of cryptographic parameters. And there's a session ID. The client can resume that session. So when your web browser requests an encrypted page, he'll go back to that same server to get images and things. And instead of conducting a whole handshake all over again, he'll resume that existing session on multiple connections.
Simultaneously. So in other words, that first handshake completes, and 3 more sockets instantly show up, resuming the session that's still going on the first socket.
Which is very efficient to do that. But this session resumption capability is orthogonal to renegotiation. It has absolutely nothing to do with it, but we've had a very difficult time convincing ourselves and everyone that is the case, because there's something very appealing that thinking that that resumption is related to renegotiation somehow, but in fact you can have renegotiations without resumption and vice versa. And there's no session identifier carried across renegotiation. There's absolutely nothing carried across the renegotiation, which is the problem. Which is the origin of this bug. Another term that people use is connection. Netscape defined the secure sockets layer, and everybody understands sockets as a connection-oriented protocol where the connection has a client and a server and a beginning and an end, and it's a ordered, reliable stream of data. An object-oriented API like Java will have some stream interface that allows you to read and write data, and it will probably use that same interface for a plain TCP socket as well as an SSL socket. Now, that's a good abstraction, but it doesn't handle renegotiation. And this is the important thing that I think was missing from the analysis of SSL v3, is that there's no name for this thing, which is an instance of a session on a connection. Now that renegotiation and session resumption are there, sessions and connections have this many-to-many relationship. You can have multiple sessions on one connection with renegotiation, or you can have the same session on multiple connections with resumption. But they don't give a name so that you can even talk about what it means to have an instance of a session on a connection. It's the thing that results from a successful handshake. The best term I can find is connection state, but it's not a perfect term, and it's not used consistently in the specs. Well, so this raises some issues of identity. Who are you talking to? Are you talking to the legitimate client? Are you talking to a man in the middle? Clearly, a properly authenticated server has an identity. He's established that with a certificate, and he's done that well. An authenticated client has an identity. If you supply a client cert and the server validates that correctly, then that's a good identity. But what about an anonymous endpoint, like the client side of a typical HTTPS connection?
Like all form-based auth connections, for example.
Yeah, the client's anonymous. Does that endpoint have an identity? And SSL TLS even allows anonymous connections. But do those endpoints have identities? And in what ways can identity change? If you renegotiate a connection, is that a new identity, or does it? And how does that change the properties of that? So yes and yes. An anonymous endpoint can definitely have an identity. Even an anonymous connection, the endpoints still have identities, which is kind of the opposite of anonymous. But the identity of an anonymous connection is, well, I'm actually talking to the same guy that I was talking to a few records before in the protocol. even though I don't necessarily have a name for him. It's, from byte to byte, I know that the man in the middle isn't copying and pasting or splicing these connections together and confusing me with this identity switch. But identities can change across renegotiation. You could supply a completely different cert after renegotiation, and that's one of the reasons renegotiation was invented.
So really, the question is, when across renegotiation, are you still the same entity as you were before? And this question is like completely left up in the air by the standards, and so nobody really knew. Nobody knows. In fact, today this is still a problem. If I send you a new client cert, does that mean I have more privileges than I used to, but I'm still the same guy I used to be? Or does it mean I'm fundamentally a different client because, after all, I've changed everything about my authentication with you? Good question.
Yeah, and so the people who designed the SSL TLS layer kind of threw this question up to the application layer without actually telling the application people about these issues that were involved here. But there was this implicit assumption. It's not stated much, but I think if you read between the lines, identity is additive across renegotiation, or at least it was supposed to be, so that if you receive data from an anonymous endpoint, you can then upgrade that to get some strong credentials from that endpoint and know that it was the same guy you were talking to even back when he was anonymous. And HTTPS does this regularly when client certs or smart cards storing client cert credentials are used. And so an endpoint could renegotiate, and you could supply multiple certificates, and those certificates should stack, and establish a greater, a stronger identity.
So there's been some question about why we even have this capability in the protocol to begin with, and I think it's a good question, frankly. And I'm going to hurry, by the way, because we're at about 45 minutes here. But one of the reasons was to refresh crypto keys. This is like SA lifetime and IPsec if you use that. I mean, could you actually exhaust your crypto state on the connection? That's been argued because the way TLS tends to be used for ephemeral connections, particularly in HTTP, that maybe that doesn't make a lot of sense. Another reason had to do with changing the cipher spec. So say you want to have certain subdirectories on your server, use super duper 256-bit AES plus SHA-256 or something, and everything else is using, whatever, 128-bit crypto.
Well, this was back when the U.S. government was restricting the export to 40 bits of encryption. You could get a special certificate if you were in the financial industry to put on your server that indicated that you could then renegotiate up to a stronger level of encryption.
By the way, anybody here used server-gated crypto certs? 0, yeah.
Right. So it wasn't used much, and as we know, features that don't get used much and are still hanging around can be a source of bugs. The third reason, and I think this was the most compelling case that the two guys next to each other on the cube were chatting about, which was to allow specifying the requirements for whether or not you required a client cert on your site to be done dynamically, so that the server could look at the URL that you were requesting and say, oh, that subdirectory, I need to require a client cert. I'll ask for a renegotiation, and in that renegotiation, I'll insist on getting the client cert. I think that was Netscape's business case, and that's the most commonly used case today.
If you don't do it this way, then you have to ask for a client cert on the initial page presentation, which means nobody wants to do.
Whenever somebody comes to your home page, it may pop up a dialog box in their browser. That's not going to pass. And then there's this other justification that people give, which is to protect the client certificate, because if you get the client certificate in a renegotiation, it is encrypted, and so you're not going to see it in a plain Wireshark capture. I think, to me, this is a questionable justification. A certificate's supposed to be a public key, right, which means you're supposed to publish it. But I think people put stuff into their certificates that they would rather keep private, like names, addresses, phone numbers, that type of thing. But this only protects against passive eavesdropping, because realistically the client app will provide that client certificate if the man in the middle just asks nicely for it. The client doesn't have a chance to strongly authenticate the server before the client is forced to produce his client certificate.
That capability is used in Tor, by the way. Tor masks identities this way.
Yeah. So the basic attack I came up with, there are two basic attacks. There's the blind plaintext injection. We showed that packet capture. And then there's client cert stealing, so that a man in the middle can, if a client has client certs configured, and the web browser may be configured to send these automatically if you just check the "Don't Bug Me Anymore" box. The man in the middle can take the client cert authentication and forward it to any server that he wants. But the main attack is this blind plaintext injection. So the attacker can insert a little bit of plaintext at the specific point at the beginning of the SSL protocol stream.
And we call it blind because the attacker still can't read the SSL stream. There's a set of crypto keys that's been negotiated that the attacker, the man in the middle, doesn't have. So the vulnerability is that the bad guy, net, can insert plaintext.
Yeah, and so this was a limited capability, and it was rather unusual. I don't know that there have been a lot of bugs that allowed this specific kind of capability, and some protocols are affected worse than others. HTTPS is one of the ones that's affected particularly badly, and it's a relatively important case because it allows the attacker to steal the cookies, like the session cookies of the client.
You steal form inputs this way. You can steal, if you're using hidden input for state tracking. If you're just logging in the first time, you've got a username and password on a web form. That's a post variable, and the bad guy can steal that.
And some of the protections against CSRF help. Some of them don't. In this case, the server sees the renegotiation, and the client does not. But the server may even be the one who requested the renegotiation, so it doesn't look unusual to him at all. But one of two things need to be the case in order for this attack to be practical. Either the server accepts the client-initiated renegotiation, and we've seen that OpenSSL does that by default, or did until recent patches, or the server can be tricked or provoked into requesting the renegotiation himself, and the attacker may be able to do that by just requesting an URL from the correct subdirectory to ask for a client certificate or something like that.
You're gonna hit that.
Now, the redirection of the client certificate will come from any client that will provide or will authenticate with a client certificate. That can be redirected to any TLS server on the internet that will accept that certificate, and it will retroactively authenticate. Well, this says the client's request, but it's really the man in the middle's request. This is potentially a big compromise for things like smart cards that are used to log into the more secure websites. One feature here is that the client doesn't see the result. The client may see a broken image or something very small. So what are some mitigations? Why don't we just get rid of renegotiation entirely, Steve?
Good question. Why don't we just get rid of renegotiation?
I don't know.
Well, it
maybe
turns
the next
out
slide will tell us. That would be easy, right? That's what most people expected.
And it generally would work.
Yep, it would work, right? But it's really bad. When the first round of patches did this, it just disabled renegotiation outright, and it broke stuff. Some things that depend on renegotiation are Tor. Tor was not actually vulnerable beforehand, just kind of because of the accident and of their design and the care that they took. It didn't seem to be vulnerable to this attack. Web services.
Yeah, so, basically, if you're using web services that aren't authenticated inside the message, like SAML or something, then this is potentially a very bad deal. And particularly if you're using client certificates to secure your web cert, and you're running IIS in default mode, you're always going to be asked for renegotiation. So you can't just kind of turn it off because your web services will break.
So the ironic thing here is that if OpenSSL doesn't feel a great motivation to fix renegotiation correctly and just ships a patch to say disable renegotiation entirely, and their customers aren't complaining, well, Microsoft shops can just switch to using integrated auth inside of a domain. That'll still be pretty secure. without the renegotiation, but it's the cross-platform interoperable stuff that needs client cert authentication the most. Another thing is smart cards. We mentioned those. Some deployments of smart cards have millions of cards and thousands of servers, and they're used for disproportionately for high security stuff. So the only correct fix is to fix renegotiation. It's got to be fixed, and what that involves is restoring this guarantee of continuity of identity. The idea that the guy who's on the other end of the SSL connection now is the same guy as was on at the beginning of establishing the connection. And you had that guarantee back with Secure Sockets Layer version 2, and it silently went away. But it was never stated in any engineering documents that we've come across. It was so obvious and implicit, I think, in SSL v2 that no one deeply questioned whether this continuity of identity guarantee persisted in SSL v3 and TLS. And there were multiple security reviews of SSL v3 and TLS that didn't spot this bug. I think, maybe if there had been more explicit requirements set out, even the obvious ones, this would have been caught sooner.
We're really short on time, so we should probably go fast through the stuff that didn't work.
So one particular mitigation would be at the record layer, have the renegotiated keys depend on both the new and the old key material. And this might be as simple as replacing an equal sign with an XOR equals. So when the new key material gets written into the right place, it gets XOR'd in. And this was my idea. I thought it was a great idea, but it's too good to be true. There's an API called PKCS11 that doesn't support that change, and that API is burned into silicon, really. Another method would be to inject the previous finished message on that connection into the beginning of the handshake when you're constructing the hash to send the next finished message. This is a technically good solution, and it doesn't require any new protocol structures, and it only requires the client or the server to patch in order to be secure. But it wouldn't be deployable by some sites for a long time. For one thing, it would break a lot of existing stuff. It would not have a compatible mode or a backwards compatible transition period that administrators could configure. And because it changed the crypto calculations even a tiny bit, that would trigger some sort of formal cryptographic review process. We heard from some users, and that could take years, to get through that kind of committee. So the project that we pulled together had this proposal, which was to define a new TLS extension. Remember, some versions of SSL v3 allowed extensions, and everything forward allowed it, but nobody had used it seriously for anything critical. They would require an extension for something security dependent, and the client and the server would cooperate with this extension. They'd send what they saw as the contents of the finished message from the previous handshake on that connection.
So, of course, if you're a server under attack, you saw a previous handshake, and if you're the client in that same connection, you didn't see a previous handshake. So you'll get your server hello back from the server when you try to negotiate with them, and it will be non-empty, and you'll know something bad has happened.
Yeah, but this requires both the client and the server to patch, so they cooperate together to eliminate the possibility of the man in the middle. RFC 5746.
Just published 2 weeks ago, 3 weeks ago, something like that.
Yeah, Opera was the first vendor to ship, and way to go, Opera. Mike'sToolbox.org was the first website to implement this. Mike has his own SSL stack, and so that was useful for testing. OpenSSL 098M implements this, and that was released
That shipped like a week ago.
I think it was a couple days ago. I mean, we don't know when it shipped exactly because the website was down during that time. Firefox has some alpha or beta code, and we know that other vendors have internal code, but it will take them months to regression test it and ship it. Additional resources. There's the IETF TLS mailing list. Anybody who's interested in discussing SSL TLS and the evolution of that and related protocols is welcome to participate in the IETF, and just by being a part of that mailing list, you actually get a vote in the future direction of that spec, for better or worse. We also have a list called Mogul Open, and we'll discuss, say, attacks on SSL TLS that maybe aren't so appropriate for the IETF list itself, but just security discussion related to TLS can take place there. At Foam Factor, we maintain a page which is the status of patches and for different vendors. I have a blog, and Steve has a blog, and we're discussing this subject there frequently.
I think that is it. We're a little over, but if there are any questions, if they're going to let me.
Yeah. Or come grab us in the next couple of days and ask us, and thank you very much.
Okay. Steve, Marsh, thank you very much. It's always interesting to get the stuff from the people that discovered it and not just read other papers. So thanks a lot.